So we're going to start with Chapter 4, Section 6. Direct proof in counterexample 6, floor and ceiling. Okay. Imagine a real number sitting on a number line. The floor and ceiling of the number are the integers to the immediate left and right of the number. Unless the number is an integer, in which case its floor and ceiling are both equal to the number itself. Many computer languages have built-in functions that compute floor and ceiling automatically. They're convenient to use when writing certain kinds of computer programs. These concepts are important in analyzing the efficiency of many computer algorithms. So, graphically, this is how you could see the floor and the ceiling. If n is an integer and x lies between n and n plus 1, the floor is n and the ceiling is n plus 1. Symbolically, floor of x equals n if and only if n is less than or equal to x and x is less than n plus 1. The ceiling is the opposite. If n is an integer, the ceiling if n is an integer, it is the ceiling of x if x lies on the number line between n minus 1 and n. So symbolically, x is a real number and n is an integer, then the ceiling of x equals n if and only if n minus 1 is less than x, which is less than or equal to n. So basically it's rounding up or rounding down. Compute the floor and ceiling of each of the following values of x. (25 divided by 4). The floor would be, what, 6? Something like that? Yes, and the ceiling would be 7. The floor of 0.999 would be 0. The ceiling would be 1. The floor of negative 2.01 would actually be negative 3. It's the next integer to the left on the number line. So its magnitude is greater than greater than x. And the ceiling would be minus 2. So there you go. There's the math for all those. Okay, example, an application. 1,370 students at a college are given the opportunity to take buses to an out-of-town event. Each bus holds a maximum of 40 passengers. For reasons of economy, the leader of the event will send only full buses. What is the maximum number of buses the event leader will send? Anybody got a calculator handy? There's 1,370 divided by 40? 34? 34 buses, okay. If the event leader is willing to send one partially filled bus, how many buses will be needed to allow all the students to take the trip? One additional, so it would be 35. Yeah. Yeah. So is the following statement true or false? For all real numbers x and y, the floor of x plus y equals the floor of x plus the floor of y. Is that true or false? By counterexample, it could be shown to be not true if you use x and y as being 1/2. The floor of 1/2 is 0. The floor and 1/2 would be 0 here. The floor of 1/2 plus 1/2 would be 1.
Are those brackets or?
That's the floor symbol. It's let me draw it a little bit larger. It's no, it's not. It's not a bracket. It's like, and then you put the x in here. Yeah, but 1/2 plus 1/2 equals 1. The floor of which is 1. 1/2 the floor of 1/2 would be 0 and 0. So 1 does not equal 0. So it would be false by counterexample. Don't do it to me. Thank you. All right. So yeah, using the counterexample of 1/2 shows that it is not always the case that the floor of x plus y equals the floor of x plus the floor of y. To arrive at this counterexample, you could have reasoned as the follows. Suppose x and y are real numbers. Must it necessarily be the case that the equation is true, or could x and y be such that x plus y, the floor of x plus y, does not equal? Imagine various values that the various quantities could take. For instance, if both x and y are positive, then floor of x and floor of y are the integer parts of x and y, respectively. So is x, the floor of x equals the floor of x plus the fractional part of x, and y equals the floor of y plus the fractional part of y, where the term fractional part is understood here to mean the part of the number to the right of the decimal point when the number is written in decimal notation. Thus, if x and y are positive, x plus y equals the floor of x plus floor of y plus the sum of the fractional parts of x and y. But also, x plus y is equal to the floor of x plus y plus the fractional part of x plus y. These equations show that if there exist numbers x and y such that the sum of the fractional parts of x and y is at least 1, then a counterexample can be found. So the counterexample of x and y both equaling 1/2. Prove that for every real number x and for every integer m, the floor of x plus m equals the floor of x plus m. So begin by supposing that x is a particular but arbitrarily chosen real number, and that m is a particular but arbitrarily chosen integer. Show that the equation is true, then it is reasonable to give one of the quantities a name, like x is the floor of x equals n. By definition, n is an integer, and n is less than or equal to x, and less than n plus 1. This double inequality enables you to compute the value of the floor of x plus m in terms of n by adding m to all sides. Thus, the left-hand side of the equation to be shown is the floor of x plus m equals n plus m. On the other hand, since n equals the floor of x, the right-hand side of the equation to be shown is is the floor of x plus m equals n plus m also. Thus, the floor of x plus m equals the floor of x plus m. So this discussion, for every the theorem 461, for every real number x and every integer m, the floor of the quantity x plus m equals the floor of x plus m. Theorem 462, the floor of n minus n over 2 for any integer n, the floor of n over 2 equals n over 2 if n is even, and n minus 1 over 2 if n is odd. Yeah. Yes.
They were given this to prove this right. Would it be okay
You'd have to state the reason how you got the counterexamples, and like they explained in the previous slides, how you would come to conclude that there were counterexamples, and what would those what would the characteristics be of those counterexamples. At least that would help. I suppose having a counterexample would be sufficient for disproving something. Okay, direct proof and counterexample. Given any integer n and any positive integer d, the quotient remainder theorem guarantees that the existence of unique integers q and r, such that n equals dq plus r, and r is less than or equal to less than d and greater than or equal to 0. The following theorem states that the floor notation can be used to describe q and r as follows. Q equals the floor of n over d, and r equals n minus d times the floor of n over d. Thus, if on a calculator in a computer language, floor is built in but div and mod are not, div and mod can be defined as follows. For a non-negative integer n and a positive integer d, n div d equals n over d, the floor, and n mod d equals n minus d times the n over d, floor. Note that d divides n if and only if n mod d equals 0. In floor notation, this means that D divides N if and only if N equals D times the floor of N over D. Okay. So theorem 463, if N is any integer and D is a positive integer, the quotient remainder theorem can be expressed in terms of the floor values of N over D for calculating the Q and the R. Let's see here. Use floor notation to compute 3850 div 17 and 3850 mod 17. Div 17 is just the floor of the 3850 divided by 17, which is 226. And the 3850 mod 17 is equal to 3850 minus 17 times 226, which is 8. So that's it for that one. I told you these were brief sections. Huh?
I think it was that brief.
Uh,
Oh, they're like 57 slides.
huh?
Oh, they're 57 slides.
23. 23.
No, I'm saying the other ones are not.
Oh, yeah. This one was only 23, so. Let's see here. Now we'll go to 7. Okay. Now we're going to get into something a little different. The past 6 sections have been on direct proofs. This is going to start with indirect. Start our discussion of indirect argument, contradiction and contraposition. Yeah. Contrapositives. Yeah. Indirect proofs are more roundabout. One kind of indirect argument or proof, indirect proof is argument by contradiction. Is based on the fact that either a statement is true or it is false, but not both. So if you can show that the assumption that a given statement is not true leads logically to a contradiction, impossibility, or absurdity, then that assumption must be false, and hence the given statement must be true. This method of proof is also known as reductio ad impossible or reductio ad absurdum, because it relies on reducing an assumption, a given assumption, to a impossibility or absurdity. Method of proof by contradiction. Suppose the statement to be true is to be proved is false. That is, suppose that the negation of the statement is true. Show that this supposition leads logically to a contradiction, and conclude that the statement to be proved is true. Use proof by contradiction to show that there is no greatest integer. For this proof, the certain property is the property of being the greatest integer. To prove that there is no object with this property, begin by supposing the negation, that there is an object with this property. Suppose there is a greatest integer, call it n. This means that n is greater than or equal to n, small n, for every integer n, small n. This supposition leads logically to a contradiction, because the definition of odd and even If n is odd, or n is even, large n is even, there must exist an odd n, plus 1. But there can always be plus 1, therefore there is no greatest integer. The fact that no integer is both even and odd can also be deduced from the uniqueness part of the quotient remainder theorem. Theorem 4.72. There is no integer that is both even and odd. Use proof by contradiction to show that the sum of any rational number and any irrational number is irrational. Well, begin by supposing the negation of what you're trying to prove. Be very careful when writing this down and writing what this means. If you take the negation incorrectly, the entire rest of the proof will be flawed. In this example, the statement to be proved can be written formally as for all real numbers r and s, if r is rational and s is irrational, then r plus s is irrational. The negation would be of a universal statement is the existential statement. There exists a rational number r and an irrational number s such that r plus s is rational. So it follows that the starting point and what to be shown are, suppose there is a rational number r and a irrational number s such that r plus s is rational. Show that this supposition leads to a contradiction. To derive a contradiction, you need to understand what you are supposing, that there are numbers r and s such that r is rational and s is irrational, and r plus s is rational. By definition of rational and irrational, this means that there are convenient expressions that can be substituted for r and r plus s, but all you can say about s is that it cannot be written as a quotient of integers. So r equals a over b, and r plus s equals c over d. By the definition of rational. Substitute r for a over b and r plus s for c over d. Subtracting a over b from both sides gives s equals c over d minus a over b. Rewriting as equivalent fractions and then subtracting fractions with the same denominator. Now both BC and AD minus AD and BD are integers because of products and differences of integers are integers. And B times D is not equal to 0 by the zero product law, property. Hence, S can be expressed as a quotient of two integers with a non-zero denominator. So S is rational, which contradicts the supposition that it is rational. Therefore, theorem 473, the sum of any rational number and any irrational number is irrational. Argument by contraposition. A second form of indirect argument by contraposition, is based on the logical equivalence between a statement and its contrapositive. To prove a statement by contraposition, you take the contrapositive of the statement, prove the contrapositive by direct proof, and conclude that the original statement is true. So express the statement to be proved in this form. for all x and d, if p of x, then q of x. Rewrite this statement in the contrapositive form. If q of x is false, then p of x is true, is false. Prove the contrapositive by direct proof. Suppose x is a particular element of D such that q of x is false. Show that p of x is false. Okay, this is kind of messed up. I don't know what this is supposed to be saying. Prove that for every integer n, if n squared is even, then n is even. Oh, okay. Yeah, okay. If n is even, for every integer n, if n squared is even, then n is even. All right, yeah. Okay, first form the contrapositive of the statement to be proved. Contrapositive is for every integer n, if n is not even, then n squared is not even. By the quotient remainder theorem, with divisor equal to 2, any integer is either even or odd. Thus, and by theorem 472, no integer is both even and odd. So if an integer is not even, then it is odd. Thus, the contrapositive can be restated as follows. For every integer n, if n is odd, then n is squared is odd. Proposition. For every integer n, if n squared is even, then n is even. Relation between proof and contradiction and proof by contraposition. It's a mouthful. Observe that any proof by contraposition can be recast in the language of a proof by contradiction. In a proof by contraposition, the statement for all x in D, if p of x, then q of x, is proved by giving a direct proof of the equivalent statement. Okay? So for all x in D, if not q of x, then not p of x. To do this, you suppose you are given an arbitrary element of x and of D such that q of x, not q of x, is true. Then show that not p of x, this is illustrated in 4.71. Suppose x is an arbitrary element of D such that q of x, not q of x, sequence of steps, to not p of x. To rewrite the proof as a proof by contradiction, you suppose there is an x in D such that p of x and not q of x. Then you follow the steps of the proof by contraposition to deduce the statement that not p of x. But p of x, not p of x is a contradiction to the supposition that p of x and not q of x, because to contradict a conjunction of two statements, it is only necessary to contradict one of them. So this process is illustrated here. Suppose there exists an x and D such that p of x and not q of x produces a contradiction p of x and not p of x. Proof as a problem-solving tool. Okay, direct proof, disproof by counterexample, proof by contradiction, and proof by contraposition are all tools that may be used to help determine whether statements are true or false. Working with examples might have given you a sense that a statement of the form, if one thing is true, then the other is true. To explore further, imagine elements in the domain that satisfy the hypothesis. Yeah. That's kind of a guessing game. It's a matter of how you would. There's not really a systematic approach that I've ever been made aware of as to choosing which proof to use. I would start with the direct proof because it's easier to follow and easier to structure, but you might find that doesn't quite cut it, and use the different form of like contraposition might make a little bit more sense to prove directly, or yeah, like I said, I wish I could be more helpful on that one. I've never found a systematic approach to determining what proof method to use. I don't know, we might come across that somewhere in the slides, but let's see here. Ask yourself, must they satisfy the conclusion? If you can see the answer is yes in all cases, then the statement is true, and your insight will form the basis for a direct proof. If after some thought it is not clear that the answer is yes, ask yourself whether there are elements of the domain that satisfy the hypothesis and not the conclusion. If you're successful in finding some, then the statement is false and you have a counterexample. If, on the other hand, you are not successful in finding such elements, perhaps none exist. Perhaps you can show that assuming the existence of elements in the domain that satisfy the hypothesis and not the conclusion leads logically to a contradiction. If so, then you have the basis for a proof by contradiction. Alternately, you could imagine elements of the domain which the conclusion is false and ask whether such elements also fail to satisfy the hypothesis. If the answer is yes in all cases, then you have the basis for a proof by contraposition. So that's, if we had waited like 2 slides, these 2 slides were answering your question, basically. Start with a direct proof, see if you can do it that way. Look at examples. If you can find counterexamples, that would prove it to be false. And then you try examples in different combinations to see what proof would be more effective or appropriate. And that's it for that slide deck. And we're going to 8. Okay. Now we're going to indirect argument, 2 famous theorems. When mathematics flourished at the time of the ancient Greeks, mathematicians believed that any given line segment, say A and B, a certain unit of length can be found so that segment A was exactly m units long and segment B was exactly n units long for some integers m and n. Segments were said to be commensurable with respect to the special unit of length. Then the ratio of the lengths of A and B would be in the same proportion as the ratio of the numbers m and n. All right. Now it is easy to find the lines, find the lines of the segment of square root of 2. Just take the diagonal. These slides get screwed up on the screen. Yeah, still. Well, anyway, by the Pythagorean theorem, c squared equals 1 plus 1, or 1 squared plus 1 squared equals 2. So c equals square root of 2. If the belief of the ancient Greeks were correct, there would be integers m and n such that the diagonal and the side were proportionate. This would imply that c over 1 equals square root of 2 over 1 equals the square root of 2 equals m over n. But then n would be a ratio of two integers, or in other words, n would be square root of 2 would be rational. All right. Gonna prove that? All right. Well, I guess they're not going to prove it. Prove by contradiction that 1 plus 3 times the square root of 2 is irrational. Well, the essence of the argument is the observation that if 1 plus 3 times the square root of 2 could be written as a ratio of integers, then so could square root of 2. But by theorem 481, we know that to be impossible. So 1 plus 3 times the square root of 2 is irrational. Are there infinitely many prime numbers? You know that a prime number is a positive integer that cannot be factored as a product of two smaller positive integers. Is the set of all such numbers infinite, or is there a largest prime number? The answer was known to Euclid, and a proof that the set of all prime numbers is infinite. Euclid's proof requires one additional fact that we have not yet established. If a prime number divides an integer, then it does not divide the next successive integer. So for any integer a, any prime number p, if p divides a, then p does not divide a plus 1. The set theorem 484 is the infinitude of primes. When to use an indirect proof. All right. The example in this section has not provided a definitive answer to the question of when to prove a statement with a statement directly and when to prove it indirectly. Many theorems can be proved either way. Usually, however, when both types of proof are possible, indirect proof is clumsier than direct proof, like I was saying a little bit ago. In the essence of obvious clues suggesting indirect argument, try first to prove a statement directly. If that does not succeed, look for a counterexample. If the counterexample search is unsuccessful, look for proof by contradiction or contraposition. I guess this slide deck was only 14. Well, we made it through 3 sections, yeah, so start with direct proofs, then counterexamples, then move on to proof by indirect methods like contradiction or contraposition. So, more things to ponder and wrap your head around. I know it can be a lot, but we can do it. Anyway, have a good day. See you on Tuesday. Remember the proof that I posted on Canvas on Tuesday is due before class next Tuesday. So have a good day, all.